This is clear to you all?
Yes, sir.
Okay. So next is this is your dew point temperature. So everybody
क्लास में आ
have
रहे हो?
seen the dew on the grass.
क्लास में आ रहे हो कि नहीं?
Have you seen the dews on the grass in the morning? Or in the winter season, we can also see the same in the evening session also, in
Yes,
the
sir.
evening as well. So from where these dews are basically coming from? Hmm? From where these dews are
Condense हो
basically
रही है सर.
condensation of air is basically processed over there. So how the dews are basically formed? Suppose let's take an example. You have just put an this is your maybe your water bottle. You have just put this water bottle in your refrigerator in normal, like normal case. Okay. So in that case, what will happen is after some of the time, this water will be cold. Okay, it will, you will feel the colder water. Okay, but if you have the same bottle and you have put this water bottle in the freezer, this is the water bottle, and you have put this in the freezer part of your refrigerator. Okay, so what will happen? Have you observed this sometimes? Hmm? What will happen at this surface of the bottle? So there may be some of the dews. There may be certain water droplets over the surface of the bottle. Okay, so from where these water droplets are coming, this is like similar as we are discussing about these dews on the grass. So basically what will happen is suppose air will flow over this. There are two bottles. One is coming from the just a colder part of the refrigerator. That is not the freezer. This is the similar cases of your. And you have put this, let's say, for the 10 minutes only. And this bottle was you have put like 1 hour in the freezer as well. Hmm? So what will happen is this colder bottle, hmm, that is supplied by this cold, or we can say the air, normal air, the moist air from the environment, and the pressure is same. That is the pressure is P atmospheric. There is no change in the P atmosphere. Means the pressure is same. Okay. So as this air will come in contact with this, okay, this water bottle, surface of this water bottle, it may basically lose some of the energy. Okay, it may lose some of the its energy. I'm talking about in terms of the temperature. Suppose the temperature of this air, or we can say the dry bulb temperature is, let's say, 30 degrees centigrade. So after like being in contact with this bottle, what will happen is the surface temperature, or I can say the air which is leaving this bottle, may be having another kind of dry bulb temperature. That may be your 28, that may be 28, 29, or you can say 27 degrees centigrade. Okay, but what happened after this? What happened after this bottle? This may be the DBT. This is the same air which is coming in contact with this air, with this bottle, and this is the 30 degrees centigrade. But after this like being in contact with the this bottle, this dbt of this air which is coming out of this surface, this may not be the same. This is not like may not be 27, this may be 21, or this may be 20, or maybe less than that, because the surface temperature of this bottle is T surface is very low. Okay, surface is very low, and in this case T surface is low, but that is not that much low. That is T surface, you can say T surface, you can say this is low, but in this case you can say very low. Are you getting my point? Everybody getting
Yes,
my
sir.
point? Okay. So if we, because we are talking about only the moisture part of the air, means, or we can say the vapor part of the air, so we need to discuss only the TS curve, and this TS curve will only, I think we have covered this yesterday only. So this is your TS curve, and this TS curve is basically applicable only for the vapor part of the air. Okay, so let's say this is the constant, and this is, let's say this is the state of the air, means the air which we are supplying from here. So let's say this is the state of the air, and this is at a particular pressure. This is the constant pressure line, and in this case of air, suppose this is the atmospheric air. Okay, so this air, this pressure may be the P atmospheric. Okay, are you getting my point? P atmospheric, or you can say P atmospheric is the total pressure. This may be the PT, but in this PT, this air, this part is, this is the PV. PV. Okay, you getting my point? This is the partial pressure of vapor in the existing atmospheric air. Okay, so let's say this is the state. Okay, and once you are trying to cool, as I said, this is your pre-atmospheric pressure, and you are not changing the pressure. Whatever the air is coming in contact with the first bottle, the same air is coming in the contact with us another bottle. Okay, this is the one, this is two. Okay, so what you have done is, once the air being cooled because of this air, because of the surface of this is the surface, this is the surface is low, so air will be cooled, but at the same pressure. This may be the another state. This is the, let's say this is your first bottle. Are you getting my point? Are you getting?
Yes, sir.
Okay, so this one is the state of the air which is coming out of the first bottle. Okay, this is the, let's say this is the, let's say if this is the temperature, if you want to draw T, so this is the T dBT which is out of the first bottle. This is out of one bottle. Okay, and this is the existing, if it is there, so this T, this one, this is the T dBT which is just we are providing from here. This is the air which is coming now. So this is the TDBT of this. This is the initial stage of the air. Means that is without in contact with any of the bottle. Okay. So further, if we, the same air which is, let's say this bottle is not now here. So what will happen is, this air will directly will contact, be in contact with the second bottle, and the second bottle, it will basically loosen the temperature more, and once it will cross with this saturation curve, what will happen? Now this is your, this is the, this is the liquid plus vapor phase, and this is the vapor phase. So here this is the first instance of the, like, air which will start to condense it. So the whatever the like vapor part in the air, in the existing air, this atmospheric air, so it will start to condense, and this condensation will leads to water droplets over the surface. These are the surface. So this surface temperature is below that, is below that, or we can say initially, at least we can say this temperature is known as, this is known as, this is known as dew point temperature. Dew point temperature means at the constant pressure, at the constant pressure, there is a, once this state of the air which is meets or cross with the saturation curve, this is known as dew point temperature. Are you getting my point?
Yes, sir.
Okay, similarly what happens in your summer season or in the winter session, in winter season is the outside atmospheric temperature is basically below the dew point temperature. So that is why, which is whatever the air is there in the environment, so that will start condensing its vapor part. So it will basically loosen its vapor part. That is why this is more dry that is, you feel it's more dry air. You getting it? The MA is constant, that is constant. I have discussed it yesterday, but this MV is basically loosen. This part is basically loosed because of this dew point temperature. So the air mostly loses most of the like vapor part. So that is why you feel the air which is in winter season, that is more dry. You getting it?
Sir, it basically loses because there is reduction in the ambient temperature.
Yes, yes. Because it's loosen is vapor part because of this temperature of the atmospheric that is quite below this dew point temperature, and it starts to condense in the liquid part. Okay,
Yes, sir.
and that is for the unsaturated air I am talking about. Okay, so we have discussed three kind of temperature. First one is this dry bulb temperature. Suppose this is the TS diagram, this is the TS diagram, and this is the curve. And suppose this is the state of air. Suppose this is your constant pressure lines, and here this is basically give you the T dBT. And I also have discussed yesterday wet bulb temperature, and that is like that. Okay, and this is the wet bulb temperature, and this point is known as dew point temperature. And you can see by this curve you can see this T dBT is greater than T WBT, and greater than this is U dew point temperature. Is it clear? And that is all for the unsaturated air, because this, let's say, this is one situation is this is for the unsaturated. This is unsaturated air, and in this is in the superheated state. Superheated state. Are you getting it?
Yes, sir.
Okay. So next, if your situation is not unsaturated, if this is saturated, then suppose this is the curve, and this is the your TS diagram, and this is your like that. Suppose now this one position, this state of air is not in the like superheated zone, but this is in the saturated zone, or you can say this is at the saturation curve. Okay, so in this case, what you can say, this is the state, and so this would be, this is the dBT, T dBT, and this equals to T WBT, and this is equals to T dBT. Getting? If this is the same, so I also have discussed, this is your wet bulb wet bulb depression. So what will happen in this case? Wet bulb depression, this is your T dBT minus T WBT. Okay, so what will happen at the saturation state?
Zero.
This will be zero. This WBD, wet bulb depression, that would be equals to zero. And what about this relative humidity phi? What is phi? What is phi? Phi
One.
is, yeah, phi would be 100% or 1. This is 1.
Unity.
Yeah, unit. Phi is 1 or 100%, whatever you want to say. It's clear to everyone?
Yes, sir.
Okay. So next we have this is your very important part. This is enthalpy of moist air. Enthalpy of moist air. Okay. So let's say, I think we have already know this part. Suppose there is a chamber. Okay, we have a provision in it that we can make a filter of air. So let's say this is your V1 part and this is your V2 part. Okay, so what is volume? V1 means, I'm saying here volume, not velocity. This is your volume 1, and this is volume 2. So what kind of property is it? It is extensive or intensive? It is extensive or intensive? And suppose we have the same chamber. Okay, suppose we have the same chamber, and that can be like, this is not divided, this is like a three film, you can travel here there. So this is the same temperature T1, this is T2. So what will happen to this? What is the temperature? Is it a extensive or intensive? Hmm?
Sir, intensive.
Temperature is intensive unit, means there may not be any T1 and T2, but there will be exactly T, and T is the temperature of whole container. Okay, but in this case, what is the volume? Is it intensive or extensive?
Extensive, sir.
So this is your extensive property. Okay, so if you want to calculate the volume, the total volume of the container, so you have to write it like V1 plus V2. Okay, so this is the extensive property. In terms of the extensive property, what you have to do is you have to add those properties. But for the intensive, you need not to calculate the T1 and T2. But this is in the thermal equilibrium. Okay, so you can say the temperature is T. But why we are discussing this? What about enthalpy? Let's say this is the H. So what about enthalpy? Because let's say this is your chunk of mass of the air. So there is a vapor part, there is a dry air part. So how you will calculate this? So let's say H equals to, this is your total enthalpy of moist air. Moist air. Okay. So you can write it H equals to HA plus HV, and write it. Can you write that?
Yes, sir.
Okay, so and you can also write in terms of the specific enthalpy, H equals to capital H by M. Okay, and H equals to capital H equals to small m or small h. Similarly, you can write for the HA. What is HA? HA equals to MA HA, and what for this HV? This is HV equals to, this is your MV HV. Okay, so finally what we can write is H equals to, this is your MV HV plus MV HA, and for this you can write it M into, or just write nothing, that is there. This is the case. So this is the total enthalpy of the moist air, and which is the combination or the summation of the, like, enthalpy of the vapor part and enthalpy of the like dry air part. And why we are doing this? Because this enthalpy is an extensive property. This is an extensive property. I already have covered this. Why we are doing this? You can relate with this. Is it clear? Is it clear?
Yes, sir.
And I think you have remembered that why we have, what we have discussed in your specific humidity omega. What was that? That was mv by ma, isn't it? Why we are doing this? Because we have taken ma in this denominator, and I have covered why we have covered this, like why we have taken only ma, why we have not taken mv over mv plus ma. I think we have covered this, and
Yes,
we
sir.
have not taken you know, because this vapor part in the air, that is a variable component, and this ma is the fixed part. So we have to see that means what is the vapor part in the, in your moist air with respect to the dry air part, because this dry air part you can say it that may be a reference. Okay, so that is why we have taken this ma in the denominator, and we have like make it the function of the vapor part only. So similar here. So if we say, if we divide this whole equation, let's say this is equation 1, and we can divide this h divided by ma equals to, you can say, you can put it here. So you can say HA plus MV by MA, and this is your HV. Is it okay? Is it okay? And let's say this is the, let's say this equals to H equals to HA plus this. What is this? What is this?
Omega.
This is your omega HV. Okay, let's say this is equation 2. Now, what is H? This is not specific humidity. This is the total enthalpy of moist air per kg of dry air. Kg of dry air. Because this is the fixed part. This is the per kg of dry air. And what is omega? Omega is the specific humidity. You know it. And what is HA? HA is the specific humidity of the dry air part, and what is HV? It is the specific humidity of the vapor part. So you can write this again, H equals to this HA plus omega into HV. Okay. So let's first cover this part, HA. What is HA? HA, or we can say enthalpy of dry air part, and this is your HA, small HA. Okay. So how you basically calculate the enthalpy of any system? Like if there is a steam, so what you have to do? You can take, suppose let's say you generally make in Rankine cycle. Suppose this is at H1, you have to calculate. This is maybe S2. So what is that? What you do? S2 minus H1, or you can write, right? CP T2 minus T1, isn't it? You do the same thing, isn't it? Yes
Yes,
or
sir.
no? Isn't it? So in the case of this dry air, suppose there may be certain state in the PV curve. So this is not this TS curve is not here, because this is the dry part. Suppose you are in a certain state. Suppose you are in this winter session. So in this winter season, so what is there? Suppose air is at a certain state, and after like having some of the process, because we are not interested about the state. Suppose that is state H1 and this is state S2. What we are doing is, what we are interested in, we are interested in the process it undergone. Basically it is basically changing at constant pressure, it change at constant volume, at the constant temperature, whatever the process is, but it changed from process 1 to process 2, and correspondingly there is a change in temperature. Okay. So either we can take, let's say suppose we are taking this as a reference. Okay. But for this dry air, what we have to do is we have to calculate HA equals to CP, and there is a temperature difference. Temperature difference. Okay. Are you getting it?
Yes, sir.
So what is this temperature difference? This temperature difference basically let you know is how the process basically changed, or how much the difference in the temperature. So if we take this reference, suppose this H1 is here, suppose this is the H1 and this is the S2, this is the S2, but you are interested in this part, this is your S2 minus H1. Okay. And at this state 2, the temperature, let's say this is T2. At this state 1, let's say temperature is T1. Either you can write T2 minus T1, or you can say let's our state T1 equals to 0. That may be 0, because reference, that is not that you are taking reference from this difference only, you can make this reference. Okay. So if this is the T1 is 0, so this is the difference would be equal to this. That is same if you take the reference from here or you take the reference from here, that is same, na? Are you getting my point?
Yes, sir.
So what is this T? Suppose you are at a state 1 and you change from 1 to 2. So this is basically difference, and that is not need to have, we should have this in Kelvin or in Celsius, whatever the like scale you have, you can go, because this is your difference. Okay. So for the HA, you can write HA equals to, you can write CP, and let's say this is the T minus 0. We have taken this as a reference. Okay. And what is this T? This is the CP. And what is this T? If this is 0, so your air changed from this 0 to certain point, and this is the like dry bulb temperature. This is your dBT. This is equals to HA. So this is the HA part of equation 2. I think this is your equation 2. So this is the HA part. And what is CP? CP is the specific uh, heat of the air at the constant pressure. Are you getting it? You will not respond.
Yes, sir.
Yes, sir.
Next is enthalpy of vapor. What is that? Enthalpy of vapor. Okay, HV. This is the HV part. So suppose in for the vapor part, what we can do is we can draw the TS diagram. This is your TS diagram. Okay. and this is the curve. Suppose this is the state of air in the final state, okay, and this is the constant pressure lines, okay. So let's say your air is not here, air is not here, so let's say this is the reference, as I said you, as I told you in the for the calculation of enthalpy in the case of dry air. So let's say this is the, this cannot go beyond this now, because this is liquid plus vapor part. So this is, there may be some vapor, there may be some liquid in the air, that is the maximum extent that you can consider for the reference point. You cannot go beyond this. So this is your reference as we have discussed in the previous case, and this may be the final, okay. So this part is, I think you know, because there is no temperature change, there is no temperature change. So this is the latent heat part, okay. This is the latent heat part, and this is, there is a change in temperature, and this is the sensible heat part. So HV would be your latent heat plus sensible heat. Is okay. So latent heat for the vapor part, so that is fixed, you can check it. So that is 2500 kilojoule per kg, and plus this, if you do this sensible heat calculation like the same case from this point to from this point, so you can calculate, this is your Cp, this is V, Cpv, okay. This in the last case, this was Cpa, this was Cpa, okay. So this is Cpv, and this is your again T minus 0. We have taken the reference 0 in the calculation of the sensible heat. So that HV would be this is 2500, in the some of the books it may be 2470 or something like that, plus Cpv, and this is T minus, this is T, that is T only. Okay, so the total enthalpy of the air per kg of the dry air would be, this is your Cpa, this is Cpa, and T plus 2500 plus Cpv T. T means this is your dry bulb temperature, dpt, okay, and this is also the same, d bulb temperature. Is it okay?
Yes,
Is it
sir.
clear? So this is the enthalpy of the moist air, and you have to write, this is kilojoule per kg of dry air. This is not specific humidity of the moist air. This is the total humidity of the total enthalpy of the moist air with respect to, or per kg of the dry air. Okay, this, you should not be confused with this S term. Is it clear?
Yes, sir.
Okay. So next is degree of saturation. Degree of saturation. This degree of saturation is basically denoted by mu. Okay. So what is degree of saturation? What is degree of saturation? So degree of saturation, mu equals to specific humidity with respect to the specific humidity in the saturation state. Are you getting it? So what is your specific humidity? Omega equals to, what you generally write, that is mv divided by ma, or we have also simplified this, 0.622 pv over is your pt minus pv. No?
Yes, sir.
And for the ws means the specific humidity in the saturation state. Specific humidity in the saturation state. So what we can write it, for the saturation part, suppose this is your TS curve. Suppose this is your TS curve. So in this state, so let's say this is your initial state, and this is the PV curve. So this is the first part. This is the for this part. Okay, suppose this is the PV. So this may be having some of the like partial pressure PV, But if you are in down going down over here, so because your partial pressure of vapor is basically increasing, so you can say in this case 0.622, you will write here not PV, you will write PVS in saturation state divided by PT minus PVS. This is the PVS. Getting? Are you getting it? And this is at the same temperature. Means if you are here, so this is the PVS